So, but we would like to convert this information into the information that we need for this parametric representation. And so we need to know a point and the direction vector. So the point will represent by the position vector r0, and the direction vector will be rv. In this case, we actually have 2 points. So you can choose either one. It's your choice. So pick one. Let's say the first one, 3, 1, -1. So your r0 is, so you see I'm being really rigorous and pedantic here. I'm distinguishing between the point and the position vector of this point by using different brackets. The round brackets for points, the angle brackets for vectors. It's very important, as I already explained. So this is your x0, y0, and z0. And now, to find v, we can simply take the difference between the position vectors of these 2 points. Right? If you have 2 points on the line, you can surely find this vector by taking the difference between this vector and this vector. So this is v. You can write v as OP prime minus OP. So I simply take the difference from 3 to -6, and I subtract 3, 1, -1. What's the result? The result is 0, 1, and -5. So now I have found what I needed, which is I have found the point on this curve, on this line, and I have found the direction vector. And now I just put all this data into this formula. Right. So the end result is x is equal to, these are my x0, y0, and z0. So x is 3 plus, this is v, plus 0 times t, which I can just erase just like this. Y is equal to 1 plus 1 times t. Z is equal to -1 minus 5t. So that's the answer. When I say it's not the answer, it's one possible answer, because someone else could instead choose as a reference point not the first one but the second one, or take the vector v, the difference not from this to this but from this to this, or even a multiple of that. So in other words, you have to realize that there is not a unique parametric representation for a line. There are many different ways. So if you get a different answer from your friend, it doesn't mean that one of you made a mistake. It could be that both of you have the right answer. Any questions about this? Now there is another way to write the equation of a line. In general, we're going to have this formula, right? So let's focus on this formula. Suppose that a, b, and c are all non-zero. Then we can express t from each of these formulas by dividing by a, b, and c. So we can find t is equal to x minus x0 over a, t is y minus y0 over b, and t is also z minus z0 over c. But it's all the same t. So we could write the following formulas: x minus x0 divided by a is equal to y minus y0 divided by b equals z minus z0 divided by c. So that's another way to represent a line. This is the first way. And this is the second way. I would like to explain what happens if one of these numbers a, b, c is actually equal to 0, which is the case we have in this particular problem. So if a is equal to 0, then we have the equation x equals x0 instead of x equals x0 plus at. Right? So in this case, we cannot express t from the first equation because t is not in this equation. But we can express t still from the second and third equations provided b and c are non-zero. So if a is 0 but b and c are non-zero, we can write x equals x0 and y minus y0 over b equals z minus z0 over c. So we get 2 equations like this. It's not surprising that we get 2 equations. In fact, here it looks like one equation, but that's because of a sort of a nice way in which I wrote it. It's not really one equation, there are 2 equality signs. This line actually represents 2 equations. This is equal to this, and also this is equal to this. It's like 2 separate equations. And someone can say, wait a minute, it's actually 3 different equations, because it says this is equal to this is equal to this, and also this is equal to this. But the third equation follows from the first 2, because if this is equal to this and this is equal to this, then the first and the third are equal. That's the usual kind of logical implication that we have for the equality. So this really corresponds to 2 equations. 2 equations. And we can see it more clearly in the case when a is equal to 0. There are indeed 2 equations in this case. So in both cases, in the general case when a, b, and c are all non-zero, or in the special case when a is equal to 0 but b and c are non-zero, we have 2 equations describing a line. There's also a special case when both a and b are equal to 0, but c is not equal to 0. I'm not going to tell you what the answer is. You'll have to figure it out on your own. But you'll see that it's also 2 equations. And a and b and c cannot all be equal to 0, because that would mean that this vector v is equal to 0. But I insisted that this is a non-zero vector. Pick a direction vector. I have to make the same. Non-zero. For otherwise, we wouldn't be able to do this, to argue this way. What's your question? Are you explaining? Oh, great. But, sorry? If a is equal to 0, b is equal to 0, and c is equal to 0, then v is not defined. Well, v is defined, but v cannot be used in this case. V has to be a non-zero vector. Now, so you see what happened is that we found actually 2 different ways to represent a line. This is the first way, and an important feature of this first way is that we have one auxiliary parameter which we use to parameterize it. One parameter. Or we can write it in this way, which really means that we write 2 equations for this line. And now I want to remind you that when we talk about curves on the plane, I explained that there are 2 different ways to represent a curve. This is the first way, when we have one parameter. But then there is also a second way in which you have one equation. Like y equals f of x, maybe let's go to f capital not to distinguish that. Or the favorite equation for the circle, x squared plus y squared equals 1. So remember, there was exactly the same picture in the case of curves on the plane. We learned two different ways to represent such a curve. One is a parametric way, where we use one parameter, and another one is by means of an equation, and then we have one equation. So what I want to emphasize now is the dimension count. Here we talk about curves, which means dimension 1. Curves in the plane. The dimension of the curve is 1. And the dimension of the ambient space is 2 in this case. Because we talk about curves, this is about curves on the plane. I'm not going to write it down. I'm talking about, yes, I did. Curve on the plane. So the object itself is dimension 1. And its ambient, it's immersed, it's put in an ambient space, which has dimension 2. So when you parameterize it, the number of parameters is going to be equal to the dimension of your object. In this case, the dimension is 1, so there's one parameter. But the dimension of your object, the dimension of the object, as I explained earlier, is equal also to the dimension of the ambient space, minus the number of equations. In this case, we have dimension 1, which is equal to 2, which is the number of variables x and y, the dimension of the ambient space, the plane. So we have to subtract 1 to get down from 2 to 1. That means that the number of equations per curve on the plane has to be 1. That's why a circle is given by one equation, x squared plus y squared equals 1. That's why a graph of a curve is given by one equation, y equals f of x. What happens now is that instead of working on the plane, we work in space. And in space, the dimension is 3 and not 2. So the dimension of the ambient space now becomes 3. But we are still talking about curves. Well, more specifically, we are talking about lines. But lines are special examples of curves. So our object is a curve. But now, so the dimension of the curve is still 1, but the dimension of the ambient space is 3. If you want to parameterize it, you have to still use one parameter, just like for curves on the plane. That's why it's not surprising that we end up with a parametric representation with one parameter. But if you want to describe your line by equations, you have to use two equations now. Because you have to be able to come down from 3 to 1. You have to drop the dimension from 3 to 1, so you have to impose two independent equations. Right? So 1 is equal to 3 minus 2. That's the number of equations. That's why it's not surprising that we really have two equations describing this line. Well, in this case, I arranged them neatly in sort of one equation, but as I just explained to you, it's not one equation, but it's two equations. Or in that case, also clearly two equations. So the same principle that I was talking about earlier of dimension count, dimension of an object being the dimension of the ambient space minus the number of equations, still works here. And it will be interesting to see now how it works for planes. Before I get to planes, I just want to mention one thing, which is that you can be asked various questions about lines. Once you learn how to represent them, you can be asked about relative positions of lines. And what can happen with lines is that lines can intersect or not. That's one possible question. Do these two lines intersect or not? Another question is, are they parallel or not? And so, in fact, there are different relative positions that can happen. First of all, two lines can just intersect. Right? So that's a possibility. And you can easily find out whether it is the case. You simply write the equation for the first line using parameter t, and then you write the equation for the second line using a different parameter s, because these are two different lines. A priori don't talk to each other. So they have two different parameters. So what you need to know is whether for a special value, let's say this one is parameterized by parameter t, but this one is parameterized by parameter s. So you want to know whether for some t equals some special value t0, there exists some special value s, which is equal to s0, so that the resulting point is the same. And if you write this down, you will get a system of equations which may or may not have solutions, and that's how you know whether they intersect or not. The second issue, which arises here, is whether these two lines are parallel to each other or not. And that's real easy, because part of a parameterization of the line is the choice of a direction vector. Two lines are parallel if and only if the direction vectors are proportional. How do you know if they are proportional? Well, you just see if one of them can be obtained by multiplying the other one by a scalar. That scalar will be immediately determined by the first coordinates, and then you check whether it works for the second and third coordinates. And that's how you see if they're parallel or not. So questions like this, but once you have this parameterization, you can handle them. Finally, it's possible that the lines do not intersect and are not parallel to each other. It's also possible. And here's an example. So let me keep this line. So let's suppose I have this line. If I have also this line, so I mean, first of all, this line can intersect this one easily. Even if it's not in this plane, it could be in another plane. It could be a more general line, right? It can also be parallel, right? But these are not the only two choices, because it can be parallel to this plane, but not parallel to the line. So it can be like this. So if you kind of look like in this way, you see that they kind of intersect. But actually, in this place, they don't intersect because there's some distance between this line and this plane. So in this case, that will skew. And again, it's very easy to find out whether they're skew or not by using parameterization. Okay. So in the remaining minutes, I would like to talk about planes. So I talked extensively about lines, but now I want to talk about planes. Which means that now, these are objects of a different kind, right? Because now these are objects which are two-dimensional. In the case of curves, we had analogous objects on the plane, because the plane was two-dimensional, so the plane fits one-dimensional objects, curves, in a nice way. But the plane cannot fit any two-dimensional objects, except itself, right? Or maybe some, you can cut some piece of a plane, it's also two-dimensional, because it is already two-dimensional itself. But in this space, we can now have all kinds of surfaces. And again, the simple surfaces which we study are the kind of linear surfaces of planes. The question is, what is the best way to represent a plane in a three-dimensional space? So we look again at this two options. One is to parameterize. The other one is to write equations. If we were to parameterize a plane, we would need two parameters, not just one, because it's two-dimensional. But if we were to write down equations, we'll need one equation, right? Because for a plane, the dimension of a plane is 2, which is 3 minus 1. So that's the number of equations. So we need to find a nice way to write an equation. Clearly, it is more economical to represent a plane by an equation than to try to represent it in parametric form, because in parametric form we would need two parameters. Formulas would be rather complicated. But we only need one equation. So let's find a good way to write down equations for these planes. And the point is that there is a very nice way to to get to this equation, because a plane can also be determined by a vector and a point. So remember we discussed that a line can be determined by a point on this line and direction vector. In the case of a plane, there's no direction vector. If there were, it would be a curve. It would be one-dimensional. So instead of talking about the direction vector of a plane, it is much wiser to talk about perpendicular vector to a plane. So a plane, unlike a curve, is determined by a point on the plane and a vector which is perpendicular to it. So instead of vector v, which is sort of like the direction vector in the case of lines, we're going to have a perpendicular vector determined by, and I will just draw it as a picture, by a point p and a vector n. Point, vector n, perpendicular to the plane. So now how do we write down an equation? Here we use the cross product. So that's where the cross product really comes into play. Because if you have a different point p prime, and you connect these 2 points, this vector n is going to be perpendicular to this vector. You can easily see it on that, using that board. Just say. So this is your vector from p to p prime. This is your plane. This vector is perpendicular to any vector that you can have inside this plane. But the condition of being perpendicular can be expressed by using the dot product. I'm sorry, I said cross product, I meant the dot product. So I'll just write down this equation. So the equation is that n dot p prime, dot p prime is equal to 0. This is the dot product. Because remember we discussed and we agreed that 2 vectors are perpendicular if and only if the dot product between them is 0. That's what I'm writing. Now if I write n as a, b, c, and I write p prime as before as x minus x0, y minus y0, and z minus z0, and use the rule of dot product, I will find the following equation. So here you have one equation in which a, b, c, x0, y0, and z0 are given, and x, y, z are the free variables, right? And all x, y, z which satisfy this equation correspond to the totality of all points on this plane. So as promised, a plane is given by one equation, and here's a way to derive this equation. Okay? So once you have this equation, there are all kinds of questions that can be asked. For example, if you have 2 planes, are they parallel to each other or not? What is the angle between these planes? But all of this can be immediately learned from this equation by looking at it and interpreting the coefficients a, b, c, and x0, y0, and z0 as this data. Okay? So I stop here, and I want to say one thing, which is that I have posted the solutions for the homework, for the first homework set, on the B-space. And I will be posting them regularly every Tuesday night, when the last of the sections, just when the last of the sections is over. Okay? So I'll see you next Tuesday.